nanoparticles and the t-shirts of tomorrow, so I guess I'm curious.
Sorry. Welcome, and thank you all for being here. Okay, so as she said, I spent my 8-week internship at Dune Sciences. They're a small startup company who provides tools for molecular scale engineering and is also working on developing products that incorporate nanotechnology. So my internship was focused on these products of nanotechnology, and before I could really learn the specifics, it was really important that I understand the general kind of aspects of nanotechnology. So in its most basic form, nanotechnology is the manipulation or study of matter at the nanoscale, which ranges from 1 to 100 nanometers. This graph kind of shows how very, very small that is. So your average ant is about half a centimeter. This end is 1 centimeter, and that's 1 nanometer. And these are just kind of various particles that are just very, very small. So a DNA strand is 2 nanometers, and a piece of your hair is 80,000 nanometers. So this is a very small scale. This is important because when you get matter at this very, very minuscule small scale, it's when you build nanostructures or nanomaterials, the ability to control this and just the degree of precision is very, very high. And this is important because this allows just nanomaterials to have special properties, like nanotubes for electrical stuff, and they're just applied in a lot of different fields like energy, thermal, optical, medical. There's a wide range of uses for nanotechnology. At Dune Sciences, I used silver metal nanoparticles, which are just silver metal, and kind of their special property is they are antibacterial. This has a lot of uses in the medical field for coating devices that could have potentially harmful bacteria buildup. And they kill the bacteria by the silver nanoparticles release silver ions, and this comes in contact with the bacteria's membrane and just disrupts the function and stops growth. And they die because of this. So this is just a picture of, you can see the membrane and the ions are just kind of disrupting it. So at Dune, we're more concerned with odor-causing bacteria and fabric, so this is what I worked with. When you apply the nanoparticles to surfaces, which makes them antibacterial, by the Linton technology that was developed by Dune Sciences, it works by taking the silver nanoparticles and coating them with a linker. This linker attaches on to your surface, and the nanoparticles become permanently bonded. So the linkers kind of act like a seatbelt that attaches the nanoparticles onto the surface. Okay, so that's kind of the broad overview of what I did. Specifically what I did was I prepared lots of samples of Linton products, and as I said before, the purpose of this was to make antibacterial fabric. And so the last 4 weeks of my internship was spent building a machine that would dye fabric with nanoparticles, and this is just a rough schematic of that. So I prepared samples and I did lots of tests on them. So part of my research and development at Dune Sciences was to treat fabric with the Linton process, and you do that it's a chemical process that you just have a linker solution and you add silver to it, and the silver becomes coated with the linkers, and then you add the fabric and the linkers attach to the fabric. And this chemical process is so safe that a high school chemistry student can do it. And so when I first came to Dune, this Linton process was kind of limited. This is me kind of preparing a sample of fabric in a small chemistry dish, and this only yielded about 20 grams of fabric, which isn't a lot. So that kind of segued into my big project of building a dye machine. So at using chemistry that has the least impact on the environment as possible. And we did this by just using less toxic solvents and reagents and disposing of waste properly. Okay, so this is Ben Helsing, my dye machine. And at Duke Sciences, we kill bacteria with silver nanoparticles. And I don't know if you're familiar, but Ben Helsing kills werewolves and vampires with silver, so I just thought that was a good name. So Pumpkin is just basically like your normal washing machine or a commercial dye machine, except much smaller, of course. We have this aluminum tank that has holes drilled through it, and this barrel, which has holes for good water flow. And that was kind of, when I was designing this machine, I had to consider all the things that it needed to have, such as it needed to have the solution flow through the fabric to coat it with nanoparticles, and it needs to be heated and turned and be easily assembled and disassembled. So after much trials and tribulations, we finally got this thing working. So as I said, the tank and then the barrel, and then this is just a PVC pipe axle that runs through it, and we just found pins and a crank that go in and then it turns, turning it. We heat it by just using an enrichment heater, which acts kind of like just the normal elements on your stove. And it's plugged into a transformer that's plugged into the wall. And yeah, so it's heated, and yeah, that's it. So that's what I did during the last 4 weeks of my internship. But for the first 4 weeks, I prepared samples with the Linked-On technology by hand, massaging it for 20 minutes. And even though you have to stand and crank the machine for 20 minutes, you get around 1,500 kilograms of fabric as opposed to 20, so much bigger yields. So silver is naturally highly photosensitive. It was traditionally used in photography, and so when you go to the store, you don't really want to buy dirty yellow socks, and that's what happens to the fabric when it becomes coated with nanoparticles. Is it turns it's not white anymore. So a lot of my experiments were designed to kind of experiment with the discoloration and trying to find safe ways to bleach the color out. I did this by using a dye fixative, which was designed to see how fixing the color on better would affect it compared to if it was being bleached. And I also used a wetting agent, which is designed to make the coating more even. And the major experiment I was working with was developing a bleaching agent that would make the fabric white without destroying the antibacterial properties. So when I did tests to see, when I tested, we sent off fabric samples that have been bleached to see if their antibacterial properties were disrupted. And this graph kind of shows the simplified version of the results we got. So the normal fabric is 99.999% affected, and so is the fabric that had a bleaching agent applied to it. So this is probably the most exciting part of my internship because it was real results that were actually there. And the other part of this experiment was using a wetting agent, which just is designed to make the coating more even. And the only thing, this reduced amount is because without the wetting agent, we think that it might not be able to grab on as well, so it's slightly more non-antibacterial. So these other graphs are ways to measure silver, which was another big part of my internship because you won't be able to tell the antibacterial properties without knowing how much silver is in it first. So this is ultraviolet visible spectroscopy machine measurement. This is kind of a calibration curve, actually. Each curve represents a different concentration of silver solution. What the machine does is it measures the light absorbency of the silver particles, and just as the concentration increases, the measurement increases. So this is a silver selective electrode measurement. This machine measures the amount of silver ions in the solution. And although it appears to vary, all these measurements are actually within the margin of error of the device. So this experiment kind of showed me that, you know, you can't always trust your results. So this is a t-shirt that I made using my dye machine. There's a few discoloration spots, like you can see this right here, and it's kind of dark, but it's not completely even. So after I built the machine and got it working, I had to figure out the right concentrations of solution, the right amounts of fabric, and there's a lot of variables that went into creating just this machine that would work and produce good samples that could be tested. So an experiment I designed was comparing the liquor to goods ratio, which is the amount of liquor or solution to the amount of goods, which is the fabric. And I found that in this experiment I used I used a more diluted solution, and I also used a wetting agent, which is designed to make the coating more even, as I said before. What I found in this experiment is that the wetting agent doesn't have as big of an effect as the liquor to goods ratio. So the less amount of fabric you would have and the more amount of solution, the more even the coating is going to be. And that's just a basic surface area volume problem, because if you have fabric in a barrel, it's turning. The more fabric you pack in there, it's going to not get coated as more evenly. So thank you all. I would like to thank my mentors, John, Scott, Dr. Miller, and Dr. Sweeney, for just supporting me and letting me have a chance to play in the lab all day. So are there any questions? And I encourage you all to visit me on my poster if you'd like to know more. Any questions? Yes?
So did the fabrics make a difference in the adhesion? Natural fabrics or synthetics? Or
there is, I mainly worked with natural fibers, but we do polyester. I didn't really work specifically with that, but what happens is the chemistry of the process just has to be changed, like the pH level adjusted or whatever. It's just different, but the same basic idea. So. Yes?
I'm curious, you said 99.999% effective. How did you measure that?
Okay, so that was a very simplified version of the results we got back, and I'm not even sure if I can explain it accurately. The tests were done they measured the amount of bacteria left over compared to what they started with, and this was done in logarithms and with numbers. So yeah, they measured it with bacteria, and I'm not really sure how to answer that, but yeah, we didn't perform the test, we sent them off. So.
Yeah, you got it. It's such a good number. I'm like,
yeah, it's designed to show that